So I'm going to talk about how to do neural network pruning while you're training without requiring a retraining step and letting you reduce the amount of memory you're going to need during training in the future. So I'm going to talk about on-device training in the present day. So on-device training in the present day is pretty limited. You have to have really small hand-tuned models to be able to fit that model onto your device, be able to retrain it, save all your weights and activations, and update it. And one of the two major reasons for this is you have limited memory bandwidth and you have limited power, especially compared to a GPU that's used for training today. So for example, if you compare the Apple A11 SoC to an NVIDIA 1080, you have a power budget of 150 watts on that 1080 and just 5 watts on the iPhone. And then for memory, you have the same story, where you have 320 gigabytes a second of memory bandwidth, but only 26 gigabytes a second of bandwidth on the iPhone. So we have to work with just 5 watts and 26 gigabytes a second. So how are we going to reduce the memory bandwidth during training? Well, we have two targets. We have weights and we have activations. So typically these are reduced after training. It's really hard to reduce them during training. And what people have done after training, there's a couple things that are out there. So you have pruning, of course, where you remove some of the weights, neurons, reduce the number of connections in your network. This also helps sparsify your activations, which you can take advantage of. Then you have teacher-student networks, which is a little bit of a different technique, where you have a big teacher network train a smaller, lighter, faster student network, which is used, for example, for Face ID. And then you can fit that on a device pretty nicely. Then you have quantization, which we just heard about. And that actually can be applied during training. You can train quantized networks if your accelerator supports it, for example, the V100 with FP16. And then, of course, you have sparse activations that can be taken advantage of with an accelerator like EIE. So just to be clear, we're going to focus on weights in this talk. We don't address activations in this work. But reducing weights is definitely the first really important step. And we have a wish list for doing this. We want to reduce the number of weights by an order of magnitude, preferably. We really want to preserve accuracy. It's not going to be very useful if we're going to take a drastic drop in accuracy to reduce the memory bandwidth requirement of these networks. And then finally, we also want to preserve the time to convergence. And the reason for this is if it takes 10 times longer to train your network on device, well, that's also going to end up using more energy than training it on a 1080 and then putting it onto the device. So the question becomes, how are we going to apply pruning to training? Which weights do we remove? So we went and looked at the literature and said, well, why don't we try magnitude-based pruning? It's the simplest technique. It's really easy to apply. And it's very basic. You just remove the low magnitude weights and set the remove weights to 0. So we tried this. We applied it from the very first iteration of training. And as you can imagine, this didn't work very well. We only got a 2x weight reduction on MNIST, which, of course, everyone knows is not very good. And the reason for this is basically vanishing gradients. It's basically like initializing 10% of the weights. So you have this random initialization, you set 90% of your network to 0, and now you can't learn anything. If you go above 2x compression, it doesn't converge at all, because again, the vanishing gradients. So the question becomes, what do we do instead? Well, that kind of leads us to our first insight that we had. Weights are a combination of two separate things, right? They're a combination of that initial randomly generated value and the accumulated gradient over time, which we say it really does represent the learning. How far you move that weight over training tells you how important that weight is to the network, how wrong that initial guess was. And what we found is most weights learn very little. So you see here, this is in a 90,000 parameter network trained on MNIST. Almost 35,000 of these weights barely move from their initial values at all. And then we have a few weights that account for all of the learning on either side here. Those weights move very far from their initial values, which could be 0 or it could be a really high number going towards 0. Both are valid things that we want to keep. So the key takeaway from this is that we want to keep the weights that learn the most. Those are the weights that we're going to save and we can forget about everything else. So what do we do once we selected those weights? What if we set them back to 0? Because that'd be really nice. We get some computational sparsity with our memory sparsity. Well, unfortunately, this doesn't work either for pretty much the same reason as before. If you do that from the first iteration, it's really hard to learn anything. You can only really go down to about 2x weight reduction on MNIST. So what if we set them back to their initial values? Since we set them to their initial values from that first iteration, that works really well for training, why don't we set things we're going to forget about, things we're going to prune, back to their initial values? Well, then the question is, how do we store the initial values? Do we put them in memory? Well, then we're just going to use the same amount of memory as storing all the weights anyway. It's not going to be very useful. So, that leads us to our second insight, is that the initial values are drawn from a random distribution anyway. So they're generated via a pseudo-random number generator feeding into a distribution, depending on what distribution you use to initialize. And the nice thing about this is you can seed that pseudo-random number generator and make it deterministic. Use the same seed, get the same result for each weight value. And now we've just removed that need to store any of the initial weights. We don't need any storage for the initial weights. Choosing the initial random number generator is also important. You don't want to choose a really expensive pseudo-random number generator. So we went with one called XORShift. Which is basically consists of 3 shifts and 3 XORs. So it's super cheap to do even on x86. On actual hardware like an FPGA or an ASIC, it's going to be extremely cheap. So for example, it only takes 10 clock cycles on x86. And then we calculated if each operation's worth like 1 floating point add, which is an overestimation, it'd only be about approximately 6 picojoules to generate one random number at 45 nanometers. Versus accessing a single 32-bit value from DRAM, which is 640 picojoules. So you save a lot by doing this. So the key takeaways from this is that we want to focus on the gradients and not the weights to select what to prune. And we want to regenerate those initial values so we don't have to store them. So now I'm going to talk a little bit about how Dropback differs from training a standard, or the standard stochastic gradient descent process. So first, we generate those weights. We don't have to load them in from memory. Of course, we still have to save the activations during the forward pass of our training loop, calculate the error, as usual. And now we start our backwards pass, and we're going to generate those weights again. Calculate the gradients, which we can do incrementally, so you don't have to materialize the full gradient array. You don't have to store that anywhere. And then you update the track set, and the track set is where we're going to put those weight indexes and accumulated gradient values to access later on our next training loop. And to kind of make this a little bit more clear, I have another example on just a simple 3-neuron network, 6 total weights, 2 inputs, 1 output. And you notice down at the bottom here, we have our track set that we're going to fill up during our backwards pass. And so things that are going to be in green are going to be things that are generated. Things that are in red are stuff we still have to save back to memory. So starting with our input, our first layer, we generate weight 0, weight 1, weight 2, and weight 3 from our pseudo-random number generator. And we save those outputs because we're going to use them during the backwards pass. And then we move on to the output layer, generate weights 4 and weight 5, calculate our error, and now we can start our backwards pass. So in our backwards pass, this is where things get interesting, right? So we see the update to weight 4, 0. We're never going to track an update of 0. It's just not going to be important. And then you see that the update to weight 5, we've put that into our track set now. Next time we do our forwards pass, we're going to generate that initial weight 5 value, and then we're going to go do a lookup in our track set and say, hey, we have a value here, and we're going to add it to weight 5 to get the full updated weight value. Same story for weight 0. Next time we use weight 0, we're going to look in the set, see that we have an update for it, and use that to create the full weight value. Now we've filled our track set, and weights 1, weights 2, and weight 3 have updates, but they're not higher magnitude updates than anything else in the track set. So we're not going to put them in our track set. These are less important than the other weights. Next time we use them, we're just going to drop them back to their initial values, see that they're not in the track set, and continue on from there. So how does this work? Before we even get to using this on a real network, we wanted to look if this followed basically standard stochastic gradient descent to a good level. So we measured this using something called weight diffusion, which is basically how far the weights moved over time during training. And you measure this diffusion using the L2 distance of your parameter vector between each iteration. And the interesting thing about weight diffusion is that you want just the right amount. You want to follow stochastic gradient descent diffusion. If you have too high diffusion, you've modified your training a lot, you move your weight values very quickly, it's going to fail to converge in a lot of cases because you've gone off to some deep end. And then with low diffusion, this is less bad, it's just slow to learn now. And remember, we wanted to converge at the same rate as standard stochastic gradient descent. So we compared this to that first technique we talked about, just applying magnitude-based pruning to training, and we saw that that had really low diffusion, as well as really bad compression results. But So it's really slow to train. It took a really long time to train that way, which makes sense. You set so much of the network to 0, now you have a much harder training problem. We also looked at variational dropout, which is another really good pruning technique. That's train with pruning, get a pruned network after type. And that had really high diffusion. So you think it learns really quickly, and that's true for MNIST. But what we actually found when we were trying to replicate the results on C410 and ResNet is that we were unable to ever get variational dropout to converge. At least without, we tried tweaking some things, we still couldn't get it to converge. And then you look at dropback comparing to the baseline, and we have a really similar diffusion profile compared to the standard stochastic gradient descent. Your initial values start at exactly the same place, and as you update them over time, they track the L2 distance very closely. So now let's look at some actual results. So ResNet 18, probably the most interesting network to you guys. We trained this on ImageNet, and we got 11x weight reduction and matched the baseline accuracy of our chainer ResNet 18 network. So the key takeaway is we can reduce the number of weights in ResNet 18 by 11 times. Great, we've reduced the weights by an order of magnitude. We can also go a little bit higher. Say you have a really small device. You really want to reduce the network and maybe some accuracy loss is acceptable. Now we can get 23x weight reduction, 60% accuracy, and you only have to track 500,000 parameters out of the 11 million parameters in our ResNet 18 network. And again, going back to that convergence rate, for most versions or most track set sizes, we really closely follow the convergence rate of standard stochastic gradient descent. It doesn't take any longer to train with dropback compared to standard stochastic gradient descent. This is really nice. So, just to recap, we've reduced the number of weights by an order of magnitude. We've preserved the accuracy compared to standard stochastic gradient descent, and we've also preserved the time to convergence. We also tested this on a bunch of C410 networks. We tested on a modified VGG16 network that has much smaller fully connected layers and one less fully connected layer as well. DenseNet, which is a really parameter restricted network with lots of activations, and then WRN2810, which is a really high parameter network and it's really wide and lots of skip connections. And the really key thing to note here is that these numbers, these weight reduction numbers, 4.5 times for DenseNet and 7.2 times for WRN2810, to our knowledge, this is a state-of-the-art result, just even reducing the number of weights in these networks, period, with any technique. And we could do this while training without needing a retraining step or without requiring more memory during training. So in summary, dropback tracks a subset of the weights, reconstructs their initial values, and rebuilds the full weights from the tracked and initial values. So some of you might be thinking, well, how does that track set change during training? Maybe that's an interesting question. Maybe we can get a little bit more performance out of that by looking at if there's any thing we can do there. And so what we saw is that the weight selection actually stabilizes really quickly. The things that you're putting into that track set locks down really, really quickly. Your first iterations, you're swapping in 2,000, 1,500 things, 1,000 things. And this, for this example, we're tracking 2,000 things total out of 90,000 parameters. But once you get to iteration 10, iteration 25, iteration 50, you've really settled down to only swapping in the back part of that set, the really small things that are a little bit less important than the things that you've put at the front of that set, the really high value updates. So let's freeze that track set, because this is going to further reduce our writes to memory. We don't have to do any kind of partitioning or sorting or updating our data structure to keep that track set in order. We can just focus on updating the values internally. So let's freeze at iteration 50, for example. And then, all we have to do is update the values. We don't have to do any more sorting or anything. So what we found is we tested this on our reduced VGG16 network, which has a total of, I think, 14 million parameters. And then what we found is that lower compression ratios, this works really well. Freezing early is fine, which makes sense. You have a lot of track parameters, so that bottom part of your track set is just inherently less important. However, the story changes at high compression ratios. Freezing early results in a pretty significant drop in accuracy. Again, makes sense. Now we have a much harder problem selecting those parameters that are going to be in that, say 500K track set, 1 million parameter track set. That's really important to get exactly the right parameters. So you don't really want to freeze in this case, or you want to freeze in epic, 100, 200 instead of epic 5 out of 300. So, in summary, dropback prunes by training, and it will enable memory footprint reduction in the future with custom accelerators, and it will open up training on edge devices. And of course, the next step to the other part of this is that we have to address activation compression as well, which we're working on. Right.
Great, we have plenty of time for questions.
Yeah, Min-Sik Cho from IBM. So I don't know whether you are aware of the paper from Uber last year, like in strict dimension, intrinsic dimension.
Yes, I remember
So
reading
in the
it.
paper, they are claiming that actually we don't need to track ways. I mean, just like as long as you select like enough number of random ways, it will converge, and then they can. I mean, they show that like it can achieve amazing compression as well. So why do you? I mean, concerning the paper, why do you want to track here when they're claiming that you don't need to track, just like randomly selecting enough number of ways is okay?
If I remember that paper correctly, it has been a while since I read it. That paper was, focused on basically, again, figuring out the intrinsic dimension, exactly how many parameters you need to have in a network. It wasn't really focused on enabling you to train with reduced memory, which is what we're aiming for with this technique, if that answers your question.
Other questions?
Have you tried this outside of the extremely constrained case and look at sort of the, like, taking the existing big hardware and training something even bigger with it?
Not yet, and that's something we're currently looking at, definitely.
Thanks.
Okay, let's thank our speaker again.